Okay, so having 103, have 1 is equal to negative 2 plus the square root of 2x plus 7. And again, isolating the radical term. So adding 2 to both ends, so I have 3 is equal to the square root of 2x plus 7. And we have, again, we have the principal square root rule to be complied with. And so we can proceed by squaring both sides of this equation. Okay, so I have 3 squared, okay, is at 9. And squaring out the square root of 2x plus 7. Remember, you have with square roots, okay, implicitly you have the index number. The radical is going to be at 2, which you very rarely will see in any publication. So we have 9 is equal to 2x plus 7. And just taking what we have in isolating the x terms, so we have 2x plus 7 is equal to 9. And if I isolate the radical term, so we have taking 7 away from both sides, we have that 2 is equal to 2x. And we have with division by 2, okay, so we're going to have that 1 is equal to x. And so we're going to have a solution for x, which we're going to have at 1. And you can always go back and check. So you have 2 times 1 is 2, plus 7 is 9. And the square root of 9 is going to be at 3. Negative 2 plus 3 is equal to 1. So the right-hand side is equal to 1 whenever x is equal to 1. And that matches up with what we have on the left-hand side in this equation. So x equals 1 is the solution. Now for what we have in 104, okay, we have another radical equation. And for this one, okay, so we have that 6 is equal to 9 plus the square root of 5 minus 3x. Okay, so the setup is pretty much introduced like what we had presented in 103. Okay, all right, so you have 2 constants and you have a single radical term in the variable x. And just as I had isolated the square root of 2x plus 7, I'm going to do the same thing with the square root of 5 minus 3x. So if I take 9 away from both sides, so we're going to have 6 minus 9 is equal to negative 3. And we have is equal to the square root of 5 minus 3x. And now we have an even root radical with the square root of 5 minus 3x. And we have on the other side, we have a constant that is negative. And now before we had a positive 3, and we were able to follow through and solve for x since the square root, or the principal square root rule, was complied with. And we have for 104, because of the negative sign, we have violations. And again, the reduction of an even root of an expression cannot lead to a negative constant. And so we have in 104, we have no solution. Again, now you could square both sides and have an apparent solution for x, but if you were to put back into the original equation, the right-hand side would be a value that is different from 6. All right. Now, for what we have in regard to number 105, okay, now here we have the appearance of the variable. We're looking at solving to show up twice, okay, and we have M105. Okay, so we're looking at solving for the variable m. Okay, whereupon we have the square root of m plus 18 plus 2 is equal to m. Okay, so we're looking at the value or values of m, okay, that will fit into this equation. Now we have a single radical term, and I can isolate, okay, the square root of m plus 18 by moving the 2 over. So we have the square root of m plus 18 is equal to m minus 2. And I can free up m plus 18 from the radical. Again, the nature of the radical is a square root. And so I'm going to square everything that is in the equation. Okay, so we have with the square root of m plus 18 squared. So we're going to have it m plus 18, and just kind of a quick mention, okay, for the square of m minus 2. So we have m minus 2 times itself, and so we're going to have m squared. We have minus 2m, where the outside and the inside products will combine to negative 4m. And again, negative 2 times itself is going to be 4. Okay, so in taking what we have now, okay, so I have a quadratic equation in the variable m, okay, but it is not yet in standard form. That is, it's not set equal to 0. And the highest degree term, m squared, okay, that is on the left, made that on the right. Okay, so you have, now with the left, I'm going to take away those terms, so I'm going to move m by subtracting. Likewise with 18. Thus we're going to have 0 is equal to m squared. Negative 4m minus m becomes negative 5m. And we have 4 minus 18 becomes minus 14. And looking at factoring, so you have 0 is equal to, again, we have the quantity. You see on the side of addition we have m plus 2. For what we have on the side of subtraction, we have m minus 7. And setting each of the binomials to 0. Now we're going to have a couple of apparent solutions. Now for m plus 2 is equal to 0, we have that m is equal to negative 2. For m minus 7, okay, we're going to have that m is equal to 7. Now I'm saying apparent, okay, because it might be that one or maybe both stated attempted solutions will not work out. So what I can do here is that I can check what I have here. Okay. And so just looking at, okay, so for m is equal to negative 2. Again, when you're checking, you don't have to write all this out. But to see how well it all fits within the parameters of the original equation. Okay, so you had the square root of m plus 18. So with m at negative 2, so I have the square root of negative 2 plus 18 followed by the addition of 2 is equal to negative 2. Guess what? Negative 2 plus 18 is 16. Square root of 16 is 4 only. And the left-hand side we have 4 plus 2 is 6. But m, with m at negative 2, the right-hand side remains at negative 2, so we have a false statement here. And because checking out m is equal to -2 does not lead to a true statement, we have that -2 turns out to be extraneous, meaning that it's an attempted solution, but it doesn't check out thoroughly. Now for what we have on m is equal to 7, so you have the square root of m plus 18, so you have the square root of 7 plus 18, plus 2 is equal to m, which you have at 7. 7 plus 18 is 25. Square root of 25 is going to be at 5. 5 plus 2 is equal to 7. 7 is equal to 7, so that is true. And so we have that m is equal to 7, so there could have potentially been two solutions for this equation, but upon examination, okay, only 7 is going to check out. Okay. All right, now for what we have in the case of number 106, and we have for this equation, okay, so we're going from solving for m to solving for the letter n. And for what we have in this setup, okay, so you have the square root of 2n plus 29, and we have plus 3 is equal to n. Okay, so like m just moments ago, n appears twice, and okay, and we have a single radical term. And if I isolate, okay, the square root of 2n plus 29, so I'm looking at subtracting 3 from both sides. So we have the square root of 2n plus 29 is equal to n minus 3. And so we have the square root of 2n plus 29 by itself, and I can undo the presence of the radical by squaring both sides. And so for what we have here, we have 2n plus 29. And again, in the case of the square of n minus 3, so we have n squared, and we have a negative 3n and another negative 3n, so we have negative 6n. Negative 3 times negative 3 is a positive 9. Okay, so we have the establishment of a quadratic equation that is not yet in standard form. Okay, so just as I had moved the terms on the left hand side of the equation for the variable m in the previous problem, I'm going to do likewise for what I have in the letter n. Okay, so we have moving the 2n and the 29. Okay, so I'm going to have 0 is equal to n squared minus 8n. Okay, we have minus 20. And we have a factorable trinomial. So with n squared, so we have going to n and n. And factors of negative 20, that will add up to negative 8. Okay, more weight will be given to the subtraction than to the addition. Okay, so we have with the zero product property. Okay, so we have setting First of all, n plus 2 is equal to 0. We have that n is equal to negative 2. And for n minus 10 is equal to 0, okay, so you have that n is equal to 10. And again, just checking what we have. Now, if you have odd root radicals, like cubic roots, all that, you don't have to check. But in the case of even roots, it is strongly recommended that you do check. Okay, so you have, so in this one, you have the square root. 2 times negative 2 plus 29. Followed by plus 3 is equal to negative 2. 2 times negative 2 is negative 4, plus 29 is going to be 25. Square root of 25 is 5 only. And 5 plus 3 on the left, okay, comes out to 8. But we have, stuck on the right, we have negative 2, so this is a false statement. And so negative 2 strikes out. As for 10, okay, so I have the square root of 2 times 10 plus 29 plus 3 is equal to 10. So you got 2 times 10 is 20 plus 29 is 49. Square root of 49 is 7. And 7 plus 3 is 10. And that is equal to what we have on the right hand side at 10 as well. So that part is true. So negative 2 does not check out, but we do have 10 to check out for what we have in n. So we have, again, just like m earlier, in 105, we have one solution for n, not m, but n, in the case of problem 106, and that is going to be the value of 10. Okay, now in the case of what we have with 107, okay, now we have a radical equation, and this time the nature of the radical, okay, we have it to be a cubic root. And for this one, okay, so you have negative 4 times, okay, the cubic root of 2x minus 5, followed by the addition of 6 is equal to 10. And if I isolate, okay, the radical term, first of all, by undoing the addition by 6, so I can take 6 away from both sides. So we have negative 4 times the cubic root of 2x minus 5 is equal to 4. Right. Now technically you could go ahead and cube both sides, but since we have division by negative 4 is going to lead up to an integer and not a fraction. I can do here, I can just go ahead and divide by negative 4. Okay, so this is going to lead to the cubic root of 2x minus 5 is equal to 4 divided by negative 4, which will be at negative 1. Okay, now, again, an even root radical expression cannot reduce to a negative constant. But an odd root radical expression can. And so we can continue and work out and determine what we have for x. So if I cube both sides of this equation, okay, so I have 2x minus 5 is equal to negative 1. Okay, and so if I follow through, add 5 to both ends. Okay, so we have 2x is equal to 4. And we have a division by 2, so we have that x is equal to 2. And again, with odd root radicals, you don't have to go back and check as you would with even root radical expressions, just like what we have with 105 and 106. Okay, so 2 is going to be our solution in this problem. And for what we have for 108, okay, so I have another odd root radical expression. So we have negative 3 times, okay, the fifth root of 4x minus 1 followed by the addition of 2 is equal to 8. Okay, so we're going to isolate the radical. Okay, so if we undo addition by subtracting 2, so we're going to have negative 3 times the fifth root, okay, 4x minus 1 is equal to 6. Okay, and okay, so 6 over negative 3. Okay, so that's going to be an integer. So if I divide the equation by negative 3, okay, so we have the fifth root of 4x minus 1 is equal to negative 2. Okay, and I can continue since I'm having an odd root radical, which can have its expression to reduce to a negative. So if I take out the radical upon taking both sides and raising to the fifth power, so we're going to have 4x minus 1 is equal to now negative 2 to the fifth. Okay, have like negative 2 times itself, times itself, times itself, times itself, and that will be a negative 32. And looking at what we have in the mix, okay, so with 4x minus 1 equal to negative 32. Okay, so if I add 1 to both sides, so we have that 4x is equal to negative 31. And with division by 4, there is one solution for x, and that would be negative 31/4. Okay, so for this we have a non-integer, and again we had an odd root radical expression, so it's not quite so mandatory to double check again as were the cases with even root radical expressions. All right, now for what we have for special cases here. All right. Now we have in the case of 109 and 110. Okay, I think there might be a problem in the Alex set that's going to have a couple of radical expressions in the same equation. And now for 109 as well as 110, okay, we have in 109 we have the equation in terms of the variable p. 110 has the equation, in terms of the letter D. Okay, now for what we have in 109. Okay, for this one, okay, I have the square root of 8 minus p, and we have minus the square root of p plus 5. Okay, and for the difference, okay, we have is equal to 1. Okay, now this problem is kind of a different beast here. Okay, and just for some of the techniques, this will kind of give us a bit of a smooth transition once we start to look into complex numbers. Okay, so I have two radical terms, okay, in the same root. You have square root of 8 minus p, square root of p plus 5. And let's say if I isolate one of these radical expressions or terms, okay, so I'm going to get the square root of 8 minus p by itself. So what I'm going to do here is that I'm going to add the square root of p plus 5 to both ends. And upon doing so, to the left, so I'm going to have the square root of 8 minus p is equal to 1 plus the square root of p plus 5. And I can free up the 8 minus p upon squaring both sides of the equation. Okay, now for the square root of 8 minus p squared, okay, so this will come out cleanly to 8 minus p. Okay, now for squaring out 1 plus the square root of p plus 5, okay, this one does not come out quite so cleanly. For what we're going to have here, so for the square of 1 plus the square root of p plus 5, so this means we have 1 plus the square root of p plus 5 times itself. Okay. And I'm going to take what I have here and just kind of put it in FOIL manner. Okay, so you got 1 and 1 as the first set that will lead to our first product of 1. Then we have the outside terms have 1 and the square root of p plus 5. Then inside it had the square root of p plus 5 times 1. So I have another square root of p plus 5. And let me mention, okay, so you have the square root of p plus 5 times itself. I'm just going to take this just one little extra step. Okay, so again, the first product you have at 1, outside and inside products, but each have at the square root of p plus 5. And if you combine, okay, so you have repetition here, so this will be 2 times the square root of p plus 5. And for the square root of p plus 5 times itself, think of it like the square root of p plus 5 squared, which will become p plus 5. Okay. And so just putting what we have all together, you have 1 plus 5 is 6. You have plus 2 times the square root of p plus 5 plus p. Okay. So we have in terms of putting back Okay, so again, from earlier, I squared out the square root of 8 minus p, which led to 8 minus p. And then we have, to the right, we have 6 plus 2 times, okay, the square root of p plus 5. Plus p. So just looking at what we have now, again, so after all that work, we still have this radical that is left over. And if we isolate 2 times the square root of p plus 5, so I'm just going to move the 6 and subtract p. Okay, so here I have 8 minus 6 is 2. Negative p minus p is negative 2p. And we have is equal to 2 times, okay, the square root of p plus 5. Okay, if you notice, we have even coefficients throughout. So if I divide the equation by 2, okay, that's just to lower the coefficient. So you have 1 minus p is equal to the square root of p plus 5. And if we square both sides once more, and there will be no more radical left over. Okay, so for the square of 1 minus p, okay, so you're looking at 1 minus p times itself. And we have with the distribution, so you have 1 times 1 is 1. Negative p and negative p we have for the outside, the inside products. And we have negative p times negative p, so this will be p squared. And you can just write this as p squared minus 2p plus 1. Okay, so for what we have here, we have p squared minus 2p plus 1 equal to p plus 5. And so in taking what we have now and expressing what we have in standard form, okay, so take away p, and also we have taking away 5. Okay, so we're going to have p squared minus 3p minus 4 is equal to 0. And in looking at factoring this time around, so I have p plus 1 and p minus 4, and setting each of the factors to 0. Okay, so you have for the apparent solutions, okay, for p plus 1 equal to 0, so I have p equal to negative 1, and for p minus 4 equal to 0, I have an apparent solution with 4. Okay, and now just from a visual standpoint, if I were to check what I have here, so p is at negative 1. So p is at negative 1. So if you think of p at negative 1, okay, so you have 8 minus negative 1. This would translate to 8 plus 1. So that part would be at 3. Negative 1 plus 5 is going to be 4. And you have 3 minus the square root of 4. Well, guess what? Square root of 4 is going to be at 2. 3 minus 2 is equal to 1, which is equal to 1. So we would have negative 1 to check out. If I take what I have for p equal to 4, if I have p equal to 4, so I have 8 minus 4 is 4, square root of 4 is 2. 4 plus 5 is 9. Square root of 9 is going to be 3. But I have 2 minus 3. And guess what? 2 minus 3 is equal to negative 1, which does not gel because negative 1 does not equal to 1. So while negative 1 works for p, it's not going to pass muster whenever the variable is set equal to 4. So this does not check out. And so for what we have in the case of p itself, there is only one solution, and that is going to be with the number 1, minus 1. Okay, so you have p is equal to negative 1, right? And now we'll look into 110, but I tell you what, I want to go ahead and look into what are referred to as absolute value equations. Yeah, quite a few topics in each of the sections. Now for what we have in the case of crossing over to what we have with absolute value equations. Okay, just symbolic notation. Okay, so you have the absolute value of x. And you have symbolically what will look like x contained by vertical bars. Okay, and now by definition, absolute value of x. Okay, now for the absolute value of x, okay, this is going to be the number of integral steps This will be the number of integral steps that x is away from 0 on a number line. And we mentioned as well, okay, now for absolute value. Absolute value is going to be a non-negative quantity. Right. And just taking as examples, like for determining absolute value. Okay, so you have like absolute value of 14. Absolute value of 14, okay, that is equal to 14. And if I have something like absolute value of negative 20, Okay, like positive 20, negative 20 is 20 units away from 0. Okay, so absolute value of negative 20 is equal to 20. And absolute value of 0, there's no distance away from 0, so absolute value of 0 is equal to 0. Now, these are just samples of looking at absolute value. Now, in the case of what we have for absolute value equations, and we have that if we have, say, k, again, if k is a non-negative value, and we have that, okay, again, what I mean by non-negative is where k is greater than or equal to 0. And we have that the absolute value of x is equal to k. So k is not negative. Okay, it could be 0, it could be 5, could be a fraction like 7/3. And we have the absolute value of x is equal to a non-negative value. Then what you're going to have for x, okay, we have two possible values here with positive and negative k. So if the absolute value of x is equal to k, then x is equal to plus or minus k, or k and negative k. And just as samples for what we have, looking at solving for the variable in each of the absolute value equations. And we'll start out with, let's say, the absolute value of x is equal to 7. So we'll say that we have k is represented by 7. And if I undo the absolute value notation, that is, remove the vertical bars, here I can go ahead and write what I have in the solutions for x. So there'll be two numbers with an absolute value of 7. That is, you have two numbers that will be 7 units away from 0 on a number line. One is going to be positive 7 and the other negative 7. So x here has two solutions with negative and positive 7. Now let's say if we have a bit of a multi-step equation, and say that we have that the absolute value of 2x minus 7 followed by the addition of 2 is equal to 19. Okay, so for this we have the absolute value of 2x minus 7 followed by the addition of 2 is equal to 19. And let's say if I get the absolute value term by itself, so I'll just move this 2 over here by subtracting. So I have the absolute value of 2x minus 7 is equal to 17. Okay, now if you notice, you have a one-to-one correspondence between the absolute value of an expression and a constant. So you have the absolute value of x is represented by the absolute value of 2x minus 7. K is represented by 17. And if I remove the vertical bars, well, this will become 2x minus 7. And upon removal of the bars, k becomes plus or minus k. So here we have 2x minus 7 is equal to positive or negative 7. Now we're still looking at solving for x. So you have, on the one hand, we have 2x minus 7 is equal to negative 17. And at the other end, we have 2x minus 7 is equal to 17. And if we have 2x minus 7 equal to negative 17, so we'll add 7, yes.
Wouldn't it be 19?
Okay, what would happen here? Okay, now I took away 2 from both sides, so he had the absolute value of 2x minus 7 by itself, and I took 2 away from 19, so that's where that 17 came in.
I'm sorry, my eyes are bad today, apparently.
That's all right, no problem. Okay, so we got with adding 7, so we have 2x is equal to negative 10, and if I divide by 2, so we have the x is equal to negative 5. Now for what we have at the upper end, okay, so you have 2x minus 7 is equal to 17. So if I add 7 to both sides, okay, so I have that 2x is equal to 24. And so we're going to have, with division by 2, we have the x's equal to 12. So we have, in this particular case, all right, so we have x is equal to, could be negative 5, or it could be 12. Again, you can always go back and check. So if x is, let's say, if x is 12, okay, so we have in this particular case, right? So we have, yeah, so we got in this one, just to double check, so we had 2x minus 7. Yeah, so that is going to check out. So we got for this one, okay, so with 12, you have 2 times 12 is 24, minus 7 is 17. Absolute value of 17 is 17 plus 2 is 19. And then for x equal to negative 5, you got 2 times negative 5 is negative 10. Negative 10 minus 7 is negative 17. Now the absolute value of negative 17 translates to a positive 17. And we have plus 2 is also equal to 19. All right. And I had to do a little bit of refocusing, but yeah. So those numbers are going to check out. Now, and looking at what we have as another case here, and just kind of serving as a reminder. Let's say that if you have, say, the absolute value of x plus 7 is equal to negative 10. Okay, so you have absolute value of x plus 7 is equal to negative 10. And this is what we have, just serving as the ultimate reminder. Again, absolute value is going to be a non-negative quantity. Okay, so you have like absolute value of a positive is a positive. Absolute value of a negative is a positive. Absolute value of 0 is going to be 0. But there's nothing that we can take the absolute value of and it equal to a negative amount. And because we have negative 10 attempted for the value of k, it turns out that for this particular item, okay, there is no solution. Okay. And that is if you have the absolute value expression isolated and you're trying to say that k is a negative quantity, well, k cannot be negative, so automatically, okay, there is no solution. And just a little different, well, not too different, but just a little different type of problem. If we have negative 3, see, we have times the absolute value of 2x plus 6. And say we have plus 6 is equal to negative 24. Okay, now we're going to isolate the absolute value of 2x plus 6. But let me mention, okay, now this is the first of the examples where we have a numerical coefficient in front of the absolute value notation. And let me mention, okay, we had the absolute value bars, and I can see why one would be tempted to go ahead and distribute negative 3, but do not treat the absolute value That is, do not treat 2x plus 6 in absolute value bars as you would if you had 2x plus 6 in parentheses. So in other words, do not distribute negative 3 in this case. So you had to work around this one. Okay, so first of all, let's say we undo the addition of 6, first of all. So if I take 6 out, so left-hand side, and we have negative 3 times the absolute value of 2x plus 6. And we have is equal to negative 24 minus 6, which is going to be negative 30. Okay, now, it is true that the absolute value of an expression cannot be negative. But here, I have the absolute value of 2x plus 6 with this negative 3 alongside it. So I'm going to get the absolute value of 2x plus 6 by itself. So I'm going to divide by negative 3. And so with this, I have the absolute value of 2x plus 6 is equal to positive 10. Okay, so we had the so in this case, k is going to come out to 10. And once I take out the absolute value notation, again, so we have 2x plus 6 will equal to numbers that will have an absolute value of 10. And we have with the values that have an absolute value amount of 10, one is going to be positive 10 and the other is going to be negative 10. And so in specifying what we're going to have for x, so I have on the lower end have 2x plus 6 is equal to negative 10. And on the upper end I have 2x plus 6 is equal to positive 10. And for both sets of equations, okay, so I have so I have 2x is equal to 4. And from this I have x is equal to 2. And for 2x, make that negative 10 minus 6. Array that is positive 10 minus 6. So you have negative 10 minus 6. So that's going to be a negative 16. Okay, so you have x is equal to negative 8. Now it's with the other equation. Now we have positive 10 minus 6. So that is equal to 4. And with division by 2, we have that x is equal to 2. Okay. And so for what we have for x, we have x equal to negative 8 at the lower end, or possibly we have at the upper end, we had that x is equal to 2. Okay, and those will be the equation solutions that will satisfy what we have in this example. And now, and just let's say just kind of taking what we have in the mix, and tell you what, let's see what we get. And we'll take in these. Okay, let's say we have let's say we have the absolute value of x is equal to 15. And we'll say we have the absolute value of 3x plus 4 is equal to 10. And we'll say we have thirdly, okay, we have negative 4 times the absolute value of 3x minus 2 followed by the addition of 10 is equal to negative 54. Okay, so just for the next few moments, let's see what we get for x for these three items. Okay, for what we have in the case of the first item, okay, so you have the absolute value of x is equal to 15, and again, that which represents k should be non-negative, and here we have the absolute value of x is equal to k, where k is represented by 15. 15 is positive, so we are going to have solutions for x. Okay, so as we drop the absolute value notation, so we're going to have for x, okay, you're going to have the numbers that will be a distance of 15 units away from 0. So those numbers will have positive and negative 15. And I guess you can say that in a sense this type of statement is a conditional, because the absolute value of x equals 15 is going to ring true on the condition that x is either 15 or negative 15. All right, now for what we have in the second case, now we have the absolute value 3x plus 4 is equal to 10. Okay, so you have the absolute value expression by itself, and here we have k is equal to 10, which is non-negative. So we're going to have solutions for x once again. So if I drop the absolute value symbols, that is, drop the bars, so we're going to have 3x plus 4, and the result of x, or the results of x, should be that whatever we have for 3x plus 4 will amount to a value that will be 10 units away from 0 on the number line. So we could have that 3x plus 4 is equal to 10, or it could be that 3x plus 4 is equal to negative 10. Okay, and so we have with our possibilities. So if I have at the lower end, okay, so we have 3x plus 4 is equal to negative 10. And we have at the upper end, we have that 3x plus 4 is equal to 10. So we have with the equations, so for both of these, I'm going to isolate the 3x upon taking 4 away from both sides. So we have here, okay, so we have 3x is equal to negative 14. And for the lower solution we have in x, we have upon dividing by 3, we're going to have a negative fraction with minus 14 thirds. Now for 3x plus 4 is equal to 10, taking away 4, so we're going to have that 3x is equal to 6, and dividing by 3, and 3 will go into 6 2 times. So you have, for this equation, there'll be 2 possible values for x. It could be negative 14 thirds or 2. Right. Now, for what we have in the third item, so we have negative 4 times the absolute value of 3x minus 2 plus 10 is equal to negative 54. And again, there might be a tendency or temptation to distribute negative 4 over all of 3x minus 2. But again, with absolute value bars, you do not treat them as the parentheses, as grouping symbols. Okay, so just working around this. Okay, so we have, we can undo the addition of 10 upon subtracting 10 on both sides. So here we're going to have negative 4 times the absolute value of 3x minus 2 and negative 54 minus 10. Okay, so this would be a negative 64. Okay, and now to get the absolute value of 3x minus 2 by itself, again, we cannot distribute negative 4, but we can divide the whole equation out by negative 4. Okay, so the left-hand side, okay, so this will become the absolute value of 3x minus 2 and negative 64 divided by negative 4. Okay, so this will end up at 16. Okay, now so we have our single absolute value expression set equal to k, which is positive, and removing the absolute value notation. So we have that 3x minus 2 is equal to plus or minus 16. And looking at what we have for x, again we have at the lower end, we have 3x minus 2 is equal to negative 16. And at the upper, we have 3x minus 2 is equal to positive 16. And so upon looking at adding 2 to both sides, okay, we're going to have that 3x is equal to negative 14. And we have a division by 3. Again, so we're going to have another x equal to negative 14 thirds. For 3x minus 2 is equal to positive 16. So we're going to have that 3x is equal to 18. And from this we have that x is equal to 6. And this time around, okay, so we want to have two possible solutions for x, and those will be at negative 14 thirds at the lower end. And we have at the upper end, okay, so we're going to end up with positive 6. Okay, so these are samples of what we have with absolute value equations. And now, let me, I'm going to get back to that number 110 just for next time. But I do want to mention something about radical properties. For radicals and exponents, I just want to mention, I'm just going to leave you just a few cases here, but if you have for radicals and exponents, where the exponent is going to be a fraction, okay, so you have an exponential base a to the m over n, and I wrote this in its radical equivalent. So like a to the m over n degrees equal to the nth root of a to the m. So in terms of fractional exponents, okay, now the denominator is going to indicate the type of root that we have here. And just kind of taking as examples. If I have something like x to the 3/2. Okay. And in this one case, so n is represented by 2, m by 3. So you have the second root of x to the third, or in the more common display, this is just going to be the square root of x cubed. And let's say that if we have, just to change up the variable, if I have something like y, and we'll say y to the 4/5. Okay, so here we're going to have the fifth root of y to the 4th. So here n is represented by 5, m is represented by 4. And I'll take just one more case here. If I have, let's say, like z let's say we have z to the 7/3. Okay, so here the fraction indicates that with the denominator we're going to have a cubic root, and a to the m is going to be represented by z to the 7th. So z to the 7/3 is equal to the cubic root of z to the 7th. Okay, now we will discuss that in number 110, and I can sort of use this as a bit of a bridge to what we'll be looking at as we cross over to dealing with equations that have non-integer exponents. And we have just for the ALEX, and I'll be looking at the section R4 results, but for the upcoming homeworks, okay, the ALEX homework section R5 with the quadratic and the rational equations, that will be due Monday, January the 25th. And for those items involving radical and absolute value equations, those will be due Wednesday, January the 27th. And I do have a class activity 1, okay, and this will be in ALEX, and this will go to the category that will involve class activities, and this will be just a handful of problems, and that will be due not this coming Saturday, but Saturday the 30th at 11:59 p.m. And just for what we have, just kind of a lead in with what we have had with radicals and exponents, and some of which will be non-integer in value. You can go ahead and be looking into, again, from page 70, numbers 90, 91, 93, 94, 96, and numbers 115 through 117.